Hello everyone, my name is Xinchen. My project is evaluation of AutoML systems on OpenML regression tasks. My mentors are Xinchen and Dr. Auton. So to begin with, what's an AutoML? AutoML is the abbreviation of automated machine learning. An AutoML pipeline includes a series of steps including data preprocessing, visualization, hyperparameter tuning, and model selection. An AutoML system aims to automate the search of plausible pipelines in each search space. It can help address the shortage of qualified data scientists. Currently, there are multiple AutoML systems available for use. For example, the AutonML is an AutoML system developed by the Auton Lab at Carnegie Mellon University. And on the right-hand side of this slide is the visualization of AutoML pipelines. We have the following research questions. How well does AutoML perform compared to other AutoML frameworks? And what is the performance of the different AutoML systems under different time budgets? Additionally, what is the performance of the AutoML systems under different dataset characteristics, especially the dimensionality, number of instances, and difficulty of datasets? In order to answer the above research questions, we set up the following experiments. We selected 4 AutoML systems for evaluation: AutoML, TPOT, AutoGluon, and auto-sklearn. The evaluation was conducted on 270 OpenML regression tasks. Each OpenML dataset is split into training and testing datasets. The training data is input to each AutoML system for model training and ranking. And the top pipeline of each AutoML system is used to make predictions upon the testing data. We use R² as the evaluation metric. For each OpenML task, the total number of experiments is equal to 5 AutoML systems times 3 time budgets. The time budgets are set to 60 seconds, 600 seconds, and 1,200 seconds, respectively. We are interested in the ranking statistics to compare the performance of different AutoML systems. Here are the results. This is a plot of every rank per AutoML system on testing predictions across datasets. We can see that when the time budget is set to 60 seconds and 600 seconds, the TPOT achieves the highest average rank. But when the time budget is set to 1,200 seconds, the AutoML achieves the highest average rank. We can also see that as the time budget increases, the average rankings of different AutoML systems get closer to each other. And here are the plots of every rank per AutoML systems on testing predictions versus dimensionalities or number of instances. We can see that in this region, the average rank of AutoML shows an increasing pattern when the dimensionality of datasets increases within the range of 0 to 80. We are also interested in the relationship between the performance of AutoML systems and the difficulty of datasets. In order to gauge the difficulty of datasets, we use 4 attributes: number of features, number of instances, success rate of experiments run on this specific data task, and maximum R² score achieved on the data tasks. And on these 4 attributes, we do a clustering on the datasets. And here are some plots regarding the distribution of success rates and maximum R² score over all datasets. We can see that many of the datasets actually not that difficult. It has a relatively high success rate is over 0.9, and it also has a relatively high R-square score. Some of them can have maximum R-square score close to 1. And the 4 plots at the bottom of the slides is the pairwise scatter plots regarding the 4 attributes. We choose n equals to 5 clusters. This is because when the number of clusters is equal to 5, it can achieve the highest silhouette score. And here is the result of the clustering. We do a k-means clustering and choose n equals to 5 clusters. We do a scaled clustering. And the index of the clusters are 0, 1, 2, 3, 4. Here is a summarization of the characteristics of the clusters. For example, the cluster 0 mainly contains datasets, small datasets, and simple tasks. And cluster 1 are mostly datasets of medium size and datasets of medium difficulty. Cluster 2 is some sample data extracted from the same data source, and it also contains simple tasks. Cluster 3 contains large difficult tasks, and there are only 3 datasets in cluster 3. Cluster 4 contains large datasets. And here are some plots of the AutoML ranking percentage distribution per cluster. For these two are for the 60 seconds and 600 seconds, and this one is for the 1,200 seconds. And we can see that under the time budget of 1,200 seconds, AutoML performs better on datasets with low success rate. It's mainly in cluster 1. We can see that the AutoML has a higher probability of achieving the top 1 places for datasets in cluster 1. And cluster 1 contains datasets of mainly low success rates. And we can also see that there is a large percentage of datasets in cluster 1 and cluster 3 where none of the AutoML systems can produce results. So we can see the purple region here is corresponding to rank none. This is because none of the AutoML systems can produce results. So none of the AutoML systems can receive a ranking for this task under this time budget. So since none of the AutoML systems can produce an actual result, those datasets are probably challenging data tasks and need future experiments and exploration. We also observe that AutoML did worse on data tasks in cluster 2. It has a relatively low percentage of frequency percentage of getting the first place. And in cluster 2, the data sets have relatively high dimensionality. We are interested in a subset of the original 270 regression tasks. This is because on this subset of datasets, the AutoML and TPOT use some specific algorithms. For example, for these 4 data tasks, AutoML and TPOT both use X2Trace as its core algorithm, but TPOT beats AutoML, and some of the advantages of TPOT may be significant. And for this set of datasets, while AutoML used lasso CV and TPOT used linear SVR, still TPOT beats AutoML and shows a relative significant advantage. So we want to see what's happening on the for the AutoML systems evaluated on these data tasks. So we run repeating experiments on a selected set of data tasks where TPOT shows a significant advantage of AutoML. We set the time budget to 600 seconds, and we set the number of repeated runs per AutoML per dataset to 10. we still use R-squared as an evaluation metric. So here are the results. The x-axis is corresponding to the training time, and the y-axis is corresponding to the testing score. The red dots represents the experiment datasets, data points for AutoML, and the green dots are for TPOT. We can see from these plots that while AutoML have rather stable testing score, has very low or even no variation in its testing score over multiple runs per dataset, but it has a very high variation in training time. TPOT is quite the opposite. It has very high variation in its testing score over multiple runs on a single data task, but it has lower variation in its training time. This is our future work. We want to explore the pipeline building of each AutoML system in order to identify major factors that can contribute to the performance discrepancies among different AutoML systems. And these major factors may be the core argument selection for each AutoML system, or some other steps like pre-processing or data transformation, such like this. We also like to automate the evaluation process of AutoML systems, because till now, the evaluation of AutoML systems are conducted manually, and which is rather time consuming and requires a lot of efforts. We want to automate the whole process so the end users of such a product can initialize and accomplish the evaluation process of AutoML systems with just a few clicks or one line of code. And these products, we want it to generate AutoML performance statistics, visualization plots, and diagnostic reports for the end developers of AutoML systems. At last, this work is supported by Carnegie Mellon Robotics Institute Summer Scholars Program and Auton Lab. I wish to say thank you to the RIS program organizers, Rachel and Dr. John Dolan, as well as my mentors, Xinchen and Dr. Auton for their continuous and kind guidance and support. This project is funded by DAFA D3M Melee project. Thank you.